All right, so today what we're talking about is zeros, solutions, and intercepts of a function. We're going to be talking about how to use these to help us graph and write polynomial functions. So we start with this just general equation again, which we've seen a few times now, which includes a sub n, that's like our leading coefficient, a sub 0, that's our constant term. All right. But we're just going to start with listing things like we said, zeros. We've talked about zeros, factors, and solutions, and x-intercepts. Zero, the best way to say it is like if we use some variable like k and say k is a zero of the polynomial function f. And then factor, remember we talked about like x minus k is a factor of the polynomial f of x. All right, so remember like k is a zero, that's just saying like x equals k. K is a factor, that's where we would subtract k from both sides and we get this x minus k. The other answer we talked about was k is a solution of the polynomial equation. And the equation would be f of x equals 0. Or in this case, it's f of k equals 0 because we're substituting k in. And then the last one is the x-intercept. And we're saying if k is a real number, it's possible to have imaginary numbers. I've mentioned that a couple times. But we're not going to worry about imaginary numbers in this class. We say k is an x-intercept. Of the graph. Of the polynomial function. And that means the graph passes through the point k comma 0. All right. So those are the key concepts that we've talked about before, those zeros, factors, solutions, x-intercepts. Just refreshing your memory about those things. Now, what we're talking about today specifically is the fundamental theorem of algebra, which I've hinted on this a few times. And it says this weird thing where it says, if f of x is a polynomial of degree n, where n is greater than 0, then the equation f of x equals 0, so we're finding zeros, has at least one solution in the set of complex numbers. All right. And then a corollary, which is like building off of that. So if we accept that the theorem is true, there's a corollary that says we have a polynomial degree n, and again, the same things as before. It has exactly n solutions provided, provided that each solution is repeated twice is counted as 2 solutions, each solution repeated 3 times is counted as 3 solutions, and so on. Basically, what this is saying is the degree of the polynomial is equal to the number of zeros we have. Which we've talked about a couple times, where I circle the 3 if it's a third degree polynomial, and then I'm able to say, oh, well, this is going to have 3 zeros. That's what I'm doing when I'm circling the 3 there. So it implies that an nth degree polynomial function f has exactly n zeros. All right, so a first degree polynomial should have 1 0 or 1 x-intercept. A second degree polynomial should have 2 x-intercepts. A third degree polynomial should have 3 zeros. I shouldn't say x-intercept, it should have that many zeros, because you could have a different number of x-intercepts, but you could still have that many zeros. And not all zeros are going to be real. I've talked about imaginary zeros in this class. We haven't really dove into what they look like. We're just saying, hey, there are some imaginary zeros, they exist. That's kind of what I've left it at. All right, this means that some zeros won't be x-intercepts. Okay. So now just looking at this first equation here, it says x cubed plus 5x squared plus 4x plus 20. How many zeros does it have? I just look at the 3 there and say to the third degree, this has 3 zeros. That's all I need to do. And then example 1b says, how many x-intercepts could this graph have? And it says a fourth degree. So this could have 4 x-intercepts. It might have fewer, but it could have 4 x-intercepts. Okay. Now, there's just one thing we have to be careful of, and that's called multiplicity and repeated roots. All right? And what it means is when a factor containing the same root is repeated twice or more, it's called a repeat root. And what that means is if I were to write an equation, let's zoom in a little bit here, that looks like f of x equals, let's say, x plus 4 and x minus 2, I can see, hey, this has 2 factors. It should have 2 x-intercepts. So at negative 4 and positive 2 should be my zeros, my x-intercepts. And it's going to do something in between, and it's going to go away. But that's what a single root looks like. It's just when it crosses the x-axis. Okay, let's fix that a little bit. So when it crosses the x-axis, that's what a single root looks like. That's called multiplicity 1. What happens sometimes, I could have something called a double root, and that's where if I have something that looks like f of x equals, we'll say, x plus, or x minus 1 squared, something like that, all right? And that's where this thing's going to come down. It's going to touch the x-axis, and then it's going to turn around. So it's still technically an x-intercept. I have an x-intercept at x equals 1, but I only have one x-intercept in this equation. But I have 2 zeros because it's a second degree polynomial. It's saying, hey, guess what? There are 2 x's here. All right, and they both happen to have the same x-intercept. So it touches the x-axis, but it doesn't cross the x-axis. That's what a multiplicity 2 looks like. Multiplicity 3, a triple root, could look something like this, where I say f of x equals x minus 1 cubed. So the 0 is x equals 1. And what could happen is it's going to come through here. It's going to hit right at the 1 there, and then it's going to go through. So it's going to like kind of almost slow down. I can actually draw that a little better. So it's going to kind of slow down as it's going through here at the positive 1. So it's going to be coming real fast, and it's going to take a turn and slow down, and then it's going to speed up again and keep going. It's going to look kind of weird. You've probably seen that. So it almost flattens and crosses the line. So flattens and crosses x-axis. That's what a multiplicity 3 looks like. All right, so whenever we see something that flattens and crosses, that's a multiplicity 3. The last one would be something like a quadruple root, which I could just say x to the 4th. Well, the 0 is going to be at x equals 0. And honestly, this one's a tough one because it almost looks the same as a square root function. But it's also going to kind of flatten. So let me draw that one a little better. So the x squared kind of, the x squared up above kind of comes in and goes back up. The x to the fourth is going to kind of flatten a little more than the x squared, and that's a multiplicity 4. So that one also flattens and touches and then heads back. Okay, but it does not cross the x-axis. Those are what multiplicities look like. So anytime you have an odd multiplicity, you could have multiplicity 5. It's going to slow down, flatten, and then cross. If you have an even multiplicity, like multiplicity 6, multiplicity 8, it's going to get flat right by the x-axis, and then it's going to go back up. That's what multiplicities do. So I still have 2 zeros there, but I only have 1 x-intercept. Or on this quadruple root, I have 4 zeros there, but there's only 1 x-intercept to show for it. That's what multiplicity is. Okay, so with factors, when a factor of x minus k is raised to an odd power, the graph crosses the x-axis. Versus when it's raised to an even power, the graph touches the x-axis but doesn't cross. That's the difference between an odd power and an even power. So higher powers will also flatten as they cross the x-intercept, as they cross the x-axis. Okay, now we're going to use x-intercepts to graph each polynomial function. So first, let's go ahead and plot the x-intercepts. So the x-intercepts are, let's see, I've got an x plus 3. So I could subtract 3 from both sides, and I get x equals negative 3 as a possible 0. So negative 3 comma 0 is an x-intercept. I also have this x minus 2 equals 0. I could add 2 to both sides, and I get x equals 2. So 2 comma 0 is an x-intercept. All right. And then if I wanted to find a y-intercept, I could technically plug in 0 for x and find the y-intercept as well. That might help me graph this function a little easier. And I plug in 0, and I'm going to find a y-intercept real quick. I get 1/2 times 3 times negative 2 squared, which is going to get me 1/2 times 3 times 4. And that's going to get me 6. All right. So I do 12 times 1/2, and I'm going to get, oh, it was yeah. So 12 times 1/2, that's going to get me 6. So 6 comma 0 is going to be my intercept, my y-intercept, or not 6 comma 0, sorry. It's going to be 0 comma 6 because I plugged in 0 for x. That's going to be my y-intercept. So now I can plot these points on my graph. I'm going to go ahead and label and say this is 5 and 10. This is 5 and 10, negative 5, negative 10, negative 5, negative 10. Always label your axes. I'm going to plot the point negative 3 comma 0. I'm going to plot the point 2 comma 0. I'm going to plot the point 0 comma 6. All right, that's what my graph kind of looks like. Now, the next part I want to do, I want to determine the end behavior. We've done this before. We had a quiz on it. I'm going to say as x approaches negative infinity, as x approaches the left, what's the y doing? As x goes to the right, what's the y doing? Well, in this case, as x goes to the left, the end behavior, right? This is a third degree polynomial, so it's degree 3. Even though it's in factored form, I can see I've got 1x there and I've got an x there, but there are 2 of them, so it's really 3 x's. So that's a degree 3. And I have a positive number, leading coefficient, positive LC. So that tells me as I'm going to the left side, my graph is going down. As I'm going to the right side, my graph is going up. Okay, step 3, I'm going to plot some points. And I can do this just by plugging in points. And let's see, if I plugged in -3 for x, I know I'm going to get a 0 in there. So I strategically chose that point. If I plug in 2 for x, I'm going to get a 0 there. I already know that if I plugged in 0 for x, whoops. If I plugged in 0 for x, I'm going to get a 6 for the y value. All right, if I plugged in a -2 for x, I'm going to get a 16, -2 times plus 3 is 1. 16 times 1/2, I'm going to get an 8 there. And then if I plugged in a -1 for x, I'm going to get a 9 for -1. And if I plugged in a +1, I'm going to get a 2. I'm going to get a 2 there for that value. So now I can go ahead and plug these points. I already had the -3, 0 plugged in and the 2, 0. I knew those were my intercepts. I had the 0, 6 as well. I'm going to plot -2, 8. I'm going to plot -1, 9. I'm going to plot 1, 2. It's going to look something like this. Now, I'm going to say I've got my x-intercepts. I do want to keep in mind that this one right here is multiplicity 2. Which means it's not going to go through the x-axis, it's going to touch it and then go back. So my graph's going to start somewhere over here. It's going to multiplicity 1 right there. It's going to come up here, do something, touch the x-axis, and go back up. So that way it matches its end behavior. So this right here was multiplicity 1. And it just goes straight through, which makes sense, straight through that point. This one right here is multiplicity 2, so it's going to touch it and then go back up. So that's the last step, is I'm going to draw the graph, which I just did. Okay, and that's what problem 1 should look like. All right, problem 2 is going to be a little trickier. It says 2 times x minus 1 squared times x minus 4. So first thing I want to do again is plot the intercepts. This time for my intercepts, I can see I'm going to have a 1, 0 with a multiplicity 2 and a 4, 0 with a multiplicity 1. So I'll plot those points there. I'm going to put, and I'm going to label my graph. Always important to label your graph. We'll count by 1s in each direction. Next, I'm going to determine the end behavior. As x goes to the left, what's f of x doing? As x goes to the right, which is positive infinity for x values, what's the y value doing? This one's another one where I got 2 x's and 1 x, so it's a degree 3, and it's a positive leading coefficient. So it's going to match the same thing I saw for example 1, where it should be going down on the left side and going up on the right side. Next, I'm going to plot some points for this equation. All right, so I'll plot the points. Let's just go 0, 1, 2, 3, 4, 5. I choose those values because I know the 1 and the 4 are going to be 0 already. If I plug in a 0, that helps me find the y-intercept, which I should do anyway. I should get in the habit of that. And I get a -8 there. All right. Plug in 2, I'm going to get a -4. Plug in 3, I'm going to get a -8. And if I plug in 5, I'm going to get something like 32, which is going to be way off my graph. So it's going to get off my graph in a hurry. And then I'm going to go ahead and draw my graph. So I've got some points plotted. I will go ahead and sketch this. It's coming from a negative direction. It's going to touch, that's multiplicity 2 with the 1, 0, and go back down. It's going to go to 2, -4. It's going to go to 3, -8, and then it's going to head back up. it's going to hit the axis again, and it's going to get off the paper before I cross 5. That's kind of what my sketch should look like for this particular problem. All right, so now I have 2 problems for you guys to practice. I'm going to fill them in, so you can go ahead and pause the video and try them. So pause the video now, and then I will fill it in just a minute here. So pause the video. Okay, so for problem number 1, you find your x-intercepts, negative 2, 0, 1, 0, and 3, 0. They're all multiplicity 1, so the graph's just going to shoot right through all 3 points. All right, and then I found my end behavior. It's a 3rd degree polynomial with a positive leading coefficient. So x is going to go from negative infinity on the left, or the y is going to go from negative infinity on the left side to positive infinity on the right side. And then I can go ahead and plot my points and sketch a quick graph of what my function's generally going to look like with my multiplicities all of 1. On problem 2, there is a multiplicity of 2 there. It's also a 3rd degree polynomial with a positive leading coefficient. So when I plot my points, I'm going to have 2, negative 12, that's going to be off my paper, negative 1, 0, 0, 6, 1, negative, it's going to be 1, negative 12. Oops, it should be 0, negative 6. Sorry, not 0, positive 6. 1, negative 12. And then 2, 0, and 3, 48. So it's going to shoot off the paper real fast here. It has a multiplicity 2 at the first one. So it's just going to hit it and turn around. Multiplicity 1 at the second location. And it's just going to shoot straight off the paper there. That's what this problem is going to look like when I sketch the graph. All right, so that's the idea of multiplicities. If you have an even degree, it's going to touch the x-axis and then turn around. If you have an odd degree, it's still going to go through the x-axis. And if it's a higher degree polynomial, it's going to kind of flatten as it either touches or flatten as it goes through, depending on how high, depending on whether it's odd or even degree polynomial. That covers everything for today. Your assignment is going to be practicing those things. Identify the leading coefficients, identify the degree, the leading coefficients, the end behavior, sketching a quick graph, and being accurate with your multiplicity of these equations in factored form. All right, there's 5 practice problems for you guys there. Good luck. Email me if you have any questions.